Hey all, my name is Afshan Lotfi, and I'm excited to show you Orion CLI, a better way to represent, collaborate, and reference computer-aided design with faster performance than STEP, which is the current open source CAD standard that can be used with better metadata for manufacturing and analysis tasks. And this is a push for what I hope open hardware tools should be. So let's kind of get started here. So we have some options in this Orion command here. And first things first is let's create a project. And what I mean by project is a way of representing CAD that is readable, that is revisionable, that is like full of rich data that you can just put on GitHub rather than some like giant unreadable step file. I found a example to use. It's kind of an embodiment of the open source hardware, which is someone who made open source robots. So let's kind of use that step file and convert it over to our format and kind of see where we go from here. So first things first is let's do Orion create, and let's kind of look at the options over there. So pretty much they have this option for including assets. And now what assets are is pretty much images, markdown files, and all kinds of stuff that can kind of give an outsider that's viewing your project a better insight into what's going on without having to download this giant step file loaded in the CAD program. But from just a web view, they could just view like, okay, these are all the parts. This is like how many of them there are. This is what the assembly structure is. This is what the assembly looks like. And so if you want like a bare bones project, which is the default, then you can just run Orion create. But if you actually want these rich assets, then you can go ahead and run with include assets. So let's go ahead and run that. Let's go ahead and name it to robot, and let's drag in this robot step file, and let's provide a remote Git repository. So I created a GitHub repository, and that's pretty much just the GitHub URL. So if we go here and I copy this Git URL, pretty much then it starts loading in the step file. And so what it's doing is it's loading in the step file, and it's kind of getting all the information out of it, and then it's exporting all the parts and the positions and all the assembly structures into this robot directory that's on our desktop, on top of also copying over our initial robot step file in there as well. And in the future, you can adjust where you want the path of the step file, and we'll go over the file structure right after this. Okay, so now this file structure is now created. So let's kind of look inside of this robot file structure and see what's inside of here. So first things first, there's our step file that I was talking about that gets copied over. There's a README that it generates, and actually that's really nice because it generates kind of a preview of our robot or any of our assemblies, and a little table of content here, and some information of how to git clone this repository. The next thing you'll see here is a config YAML file. And so this pretty much has the path to your CAD file. This has the name of the project. If you have a remote URL, it'll have that. And then it'll also have your options for how you want to handle certain. And so, yeah, we have this config. The next thing you'll see here is you have this inventory. And this inventory pretty much has another README file that has all of the parts in the project. So you'll have like an image of it that's really nice, and the name and any variations of it. So if you have like the same part and it has like two different colors or two different materials or whatever, it'll pretty much show up here. And variations are calculated pretty much based off of the color that it is in the CAD file. So if you have two parts that are two different colors, then it'll have two different variations of the part. And then any other metadata, if you had like a price or maybe a URL to McMaster or something that you want to include in your metadata, then you can put that in there as well. And then you also have this catalog.json file that kind of has like the whole structure of like all the parts and the variations of those parts and any other metadata that it might have. And all the parts are then stored in this parts directory that's just a bunch of brep files. And the thing that's nice about brep files is that pretty much they're all kind of plain text. They're not these binary formats. I mean, obviously they're not the most readable, but they're very Git friendly. And to the extent that like it's readable to the user, it's like, okay, well, I know the name here, and I can just refer to that name in the README. And that's why the READMEs are there, so that we can kind of refer to these breps in like a kind of more visualized format. And so you have that, and then all your assets are stored here. And then finally you have this assembly structure. So this assembly structure pretty much has like all the assemblies and sub-assemblies and parts, and all these parts are being passed by reference. So you'll have like essentially a checksum to the part, which is like it calculates based off of like the vertices and any of the variations. So if there's like two different parts and one's a different color, it'll maybe refer to it by the second variation of that part. And then it takes that part in by reference, and then it gives it a location to align it. So you can kind of see that here, and it has like this giant assembly structure here. Yeah, and so let's say that like let's go into this robot directory here, and let's say that I changed the step file, which I didn't change it, but let's say that I did, and you wanted to update this. Right now, it kind of staged all of these changes. It hasn't committed anything yet. But let's say that you did make a change. So you just do Orion revision, and it already knows that what the step file is because it has that config YAML. I think I spelled it wrong. And yeah, so now it's reading that step file back in, trying to see if there's any new changes that maybe are there. And it says that there are no changes detected, so let's not stage these changes. Okay, now we have these changes staged, and let's say now we want to deploy it. All you have to do, and you want to deploy it to GitHub or whatever Git server you want, you just do Orion deploy, and that's it. And then it's pretty much going it's saying, okay, what is your deployment message? So let's just say first, let's say initial deployment. And literally what it'll do is just go through and push those changes up using Git. So once those changes are up, it'll be on your GitHub, which is in this case this repo here. And yeah, you can kind of see all of this stuff that we saw in VS Code, and you can share this link with anyone. Now, the final thing is, okay, I want to visualize this project structure. How do I do that? All you have to do is you just say Orion display. And then what it'll do is it will tessellate this into a bunch of triangles that are readable for the tessellation viewer and render it in the browser. So it's about to finish that up. And then it opens it up into the web browser, and there you go. And now what you can do is you can do all kinds of stuff. You can go here and like explode all the parts. You can go through and like click on specific parts, see like where they are. And yeah, and you can like view different views of it. So yeah, and so this HTML file just gets generated. And the nice part is that it actually caches the tessellation. So if I run this again, it's actually going to be like orders of magnitude faster because it has actually cached everything. So yeah, that's all there is to that. And then the final thing is actually the Python API for this. So there's a CLI kind of API that you can kind of interface with it, but you can also interface with this through the Python API as well. So if we go to this assembly Python notebook, pretty much there's an example here. So there's a step file, and this is what I'm talking about with step files. It's incredibly slow to load a step file in. It takes like 6-7 seconds, and you know, for some of these giant turbine examples that I have, it even takes even longer than that. So, but with ours, which I'll show, it's just like that. Like it loads it in like very quickly because everything's by reference, and there's like not all this like weird clunk going on. And so this is how you kind of define a project here. And then this is an index, which is kind of like how it can cache and like store like, okay, what's been modified and like what parts are grouped, all that kind of stuff. And this is then taking in this CAD query assembly and reading it in. And so let's go ahead and run that. And this is like pretty fast. And then if you want to write the structure, you can just do this CAD service.write project, and I'll just write it. And look how fast that was. And then if you want to read a project, all you have to do here is you just go and read it, which is like 0.2 seconds versus 6. This is what I'm talking about speed. And then the final thing is you want to visualize the project. So you can then just load it in from the project directory, and then it'll do the whole like kind of same tessellation process, which we've already seen how it looks. So yeah, this is a really interesting tool. I've been wanting to make something like this for a while because I think that everyone's been talking about like a Git for CAD, and they're just making their own like Me Too PLM solution that's just been around forever. I figured there should actually just be an open source version that can track changes, that can store a lot of metadata, that has a very nice Pythonic API. And we're going to be using this for a lot of things later down the road. You'll have to see, but we needed kind of an underlying tech to do this all. And yeah, and so we're proud to release this alpha tonight. And yeah, thanks for tuning in.